We're going to move on to talk about spin, and more specifically, some experiments carried out by Sterngerlach in the early 1920s. These experiments are going to show spin to be one of the simplest quantum mechanical systems, and so it'll be a great way for us to first learn the rules and postulates of quantum mechanics. However, spin and the actual experimental setup for this experiment are kind of tricky, so we'll need to spend some time talking about those. In the early 1900s, there was strong experimental evidence that electrons behaved like tiny little magnets. And one way to model this is to have the charged electron spinning with angular momentum s, and this would make a little magnet. Now, viewing it like this is successful in explaining these experiments, but it can't be the final model. Okay, it's not really what's happening. A couple problems. First of all, the rate of rotation of these electrons would never change. And also the electron would have to be spinning much faster than the speed of light, at least parts of it would, in order for this to be a successful model. So we understand now that spin is more like an intrinsic quality of an electron, similar to its mass or charge. And this is strictly a quantum mechanical phenomenon. So there really is no classical analog to this. Now we're going to introduce a device, their experimental device, we're called the Sterngerlach device. And what this does is it measures the projection of a particle's spin on some axis. All right, so we're going to send particles into this machine here, and our particles we're going to model as little tiny bar magnets. Okay, so little tiny magnets with a north end and a south end. And we're going to see how they actually measure the projection of the particle's spin. So here's a picture of more simplified SG device. And so we have 3 bar magnets. Again, these are just a model of our electron, and they're close to a big north end of a bar magnet. And so we want to know is which one feels the largest magnitude of force from the big north end. So go ahead and pause, think about this one, and we can talk about it in a little bit. Okay, so here's what we're thinking. So there's 2 things going on with this problem. First thing is that we assume that the way that this works is the north sides repel each other and the north and south attract. And so if you look here at this bar magnet, the south end is going to attract if we write out that force, and the north end was going to repel. And in this case, the 2 forces, the 2 sides are about the same distance from the north end. And so they're going to feel essentially the same force, and so the net force in this case here, we would call it 0. Now let's look at C first. In C, the north end is going to feel some force. I'll draw it this big downward because this north end is going to be repelled by the really big north end, and this south is going to be attracted with some maybe a little arrow like that. So overall, my force might be like this right here. So this is the net force, approximately. Now with this one in here, it's going to be similar to that, but the forces will be a little smaller because the north is further away and the south end is closer. And so this arrow will be much closer to the same size as this one. And so there'll still be some force net down, but I'm going to draw it smaller. So the one with the largest magnitude is going to be C. And that's what's really going on here. So this bar magnet will apply a force to these things where basically the biggest force is given to be this one here. And if you look at the projection of the spin, now this is a little complicated by the fact that the electron is negatively charged, right? But if you just look at the magnetic moment of these different bar magnets, okay, something kind of like this here, we're going to end up. So this is telling us something about how aligned the magnetic moment is with an axis. In our case here, that axis would maybe be right here. Maybe we call this the z-axis. What the heck? All right, and so this device applies a very small force, 0 force on this one, which is not aligned at the z direction at all. A very large force with this one, where the magnetic moment is lined up with the z-axis, and somewhere in between for this one that's partially lined up. So now take a time, and what I've done here is the same setup. It's a simplified SG device, but we've taken the magnets and rotated them. So now, which bar magnet will feel the largest magnitude of force from the big north end? Think about this and let us know. All right, hope we got the same thing actually, but in a little bit of a different case. So again, we're sort of looking at this as, we'll call this our Z direction. Now if you look here again, this net on A is 0. The same reason. Now this one here again is going to feel the bigger difference in force. So this south end now is pushing upwards, and the north end is going to be repelled, and so overall there's some F net here, and this one in between is going to be again downwards, but at some lesser level. So again, what this device does is it finds out how aligned the magnetic moment is with some axis. And so now what's happening is these are anti-aligned with that, and so what it does is it applies a very large net force down on this one that's very anti-aligned and some smaller force here. And so basically it gives us a way to distinguish first whether it's aligned or anti-aligned with this axis, and also how strongly it's aligned or anti-aligned. And so this is the innards of the SG device. We won't deal too much with it, but you get a lot of questions, and so it's good to sort of have an idea of what's happening. So we've talked a little bit about these devices. Now let's look at the experiment. So here's our Sterngerlach device. And when measuring the projection of a particle's spin on any axis, we either find that it's totally aligned or totally anti-aligned, which is really weird, right? Because shouldn't the spin be able to point somewhere in between? Well, what we find is that, so we've got a SGZ device, so we're measuring the spin along the Z axis. We either get that it's completely aligned or completely anti-aligned, and the values we get are h bar over 2 and h bar negative over 2. H bar is just h over 2 pi, so it's just an easier way to write that. So this behavior is non-Newtonian, and what we're saying here is that spin is quantized, all right? So it doesn't come anything smaller than h bar over 2, so you can't have h bar over 4 or something like that, and here's where the quantum and quantum mechanics comes. So they did a series of different kinds of experiments with these devices, and so here we've got two SGZ devices set up next to each other. And so what we do is we send a bunch of spins into the SGZ, the first one, and ones that come out positive, all right, so their spin is aligned with the SGZ, we then put through another SGZ. And when this happens, we get 100% of them coming out of the aligned and 0% coming out of the anti-aligned. And so this is good. This, okay, I can buy this. The percentages here also are of the total entering the second device, just to be careful. Now for experiment 2, what they do is they take one device, an SGZ device, and then they take the positive, so it's aligned with the Z direction, and they put it through an SGX device. And all that is it's an SGZ device that's just been rotated a little bit, and so now it's measuring the particles in the positive and the negative direction and the X direction. All right, and so what they find is when they do this, you can't predict what each electron will do. It's going to go through, and after many measurements, it's found that 50% come out positive and 50% come out negative. So now for their third experiment, and what they do is they start with the last experiment we just dealt with. So you have an SGZ device. You have electrons coming into there, and they collect the ones that are aligned with the Z axis, and then they put them through this SGX device. And again, they find that 50% come out positive, about 50% come out negative. And so what they do is they block those ones coming out from the negative and then send ones that are coming out from the positive. So these ones are aligned with the positive x-axis, and they send them through an SGZ device, which again will remind you that these electrons are coming, their source coming into here is from the aligned with the SGZ direction. And when we do this, surprisingly, we cannot predict which electron, what it will do, and it's found that again, 50% come out positive, 50% come out negative. And so what it appears is that measuring the X component affects the state of the electrons, right? These were originally aligned with the Z-axis, but after measuring the X-axis, they no longer come out that way 100% anymore. So quantons, again, originally in the positive, I should say positive Z state, just to be clear. Measuring the X components causes the quanton to forget what Z component state it was in. And so this is similar to how the proximity detectors caused the quanton to forget that they were contributing to interference pattern in the two-slit experiment. So it's a very similar idea. And now for something very weird. So we do this exact same experiment we were doing before. So we send the particles through the SGZ, and we take the ones that are aligned with the SGZ and send them through an SGX. And of course, when we do that, 50% are in the top path, 50% are in the bottom path. But now, in this case, you recombine these two paths coming out of the SGX. And this is really important. You recombine them such that there is no way to know which is which, or another way to say it, there's no way to know which particle took the top path or the bottom path. Now that's very difficult to do, but you can do it. And if you do this and combine these two paths, you get all electrons are found to be in the positive state. And so it's effectively as if the SGX device is not here at all, or even more importantly, it's as if there was no measurement of the SGX. Of course, we know that if you measure the X component of spin, you screw up the results for the Z direction. So let's talk about this by looking back at the two-slit experiment. And so it's a very similar idea. So here we have two slits. There's two paths to get to the point that we're talking about, where there may be a constructive interference or destructive interference. And when we do this, when you have no idea which path the particle is taking, you get these interference effects. However, if you set up the proximity detectors, right, and so say you do that and the top one goes off, so we know the particle was in the top path, you destroy the interference. All right, and one way to think about this is that the quanton is forced into one of the paths. We're going to call this the collapse of the state function. And so when you force it to go into one of the two paths, the interference is destroyed and the quanton takes the top path. That's analogous to what's happening here. When there's no way to know which path is which, the two paths come together and you can have interference, just like with the two-slit effect. All right. Now, when we block the bottom path, all right, we collapse the state function and we are forcing only the quantons to come out through this path here for our experiment. And so whenever you do that, you're essentially making a measurement. We'll talk much more about this.